Okay. It is our honor to have to welcome our speaker, Professor Hao Yang, also go with name Frank Yang, from Johns Hopkins University. Frank is an assistant professor in the Department of Civil and Systems Engineering and a member of the Data Science and AI Institute. He has done a lot of research that's quite innovative, and they center around developing trustworthy machine learning and data science methods to improve the equity, safety, and sustainability of urban systems. And he also works on human mobility, transportation, and public health. And his work has developed new methods that are data-driven and centered around using new sensors and perception solutions to create an ethical and trustworthy machine learning methods and building human-machine cooperative traffic systems. Apart from research, Professor Yang is also an active member of several standing committees within the Transportation Research Board and American Society of Civil Engineers Transportation and Development Institute's AI committee. And he has earned numerous awards, including several outstanding student awards from the U.S. Department of Transportation and the Best Paper Award and Best Dissertation Award. Prior to joining Johns Hopkins University, Professor Yang has worked as research scientist in National Science Foundation AI Institute, as well as the Department of Electrical and Computer Engineering at Duke University. So without further delay, let's welcome Professor Yang, and the floor is yours. Thank you.
Thank you so much, everyone, and thank you, Maishi, for your introduction. It's quite a great pleasure and honor to share our ongoing research with Berkeley and the PATH team. And, so today's focus is actually, I think 50%, most of the 50% of our group's ongoing work, which is we try to find out a new human AI collaborative procedure based on generative AI. And that is also what we are trying to focusing on in the next 5 and even 10 years. So as Manish introduced, I'm Frank Yang, and assistant professor, Department of Civil and Systems Engineering. I'm also part of the Data Science and AI Institute. We try to mix everything. I think every corner right now is try to insert, the AI is try to insert it as every corner. So quite common right now. And so my background is a little bit mixed. That's also the motivation and reason why I'm doing research sometimes you think is quite interdisciplinary. I got my bachelor in electrical computer engineering and master and PhD from UC Washington, civil engineering in transportation. And also try to finish, after I got the PhD degree, I got the offer from Hopkins. But at that time, I was a little bit confused what kind of research I really should focusing on. I really want to hear the information and hear the thoughts from both computer science and transportation engineering. So I choose to went to Duke, and there's a National AI Institute. Try to learn from the current AI hardware, from hardware systems to the software development. And then I started my career in 2024, and also have ongoing collaborations with Amazon Machine Learning, NVIDIA team, and Microsoft Research. Actually, one of my students, and Yang Zhao, just got the Amazon PhD fellowship. He's one of the, I think, 108 total PhD fellowship funded by Amazon AI Research. It's quite an inspiring thing for us, I think. So it's pretty much about me. So right now, my group have 13 students, and we are really interdisciplinary. We come from different majors and interests, but we trying to produce a research and real world impacts from different domains. And we're not just publication papers on transportation sector. We also think about deliver our presentation and papers on nature computational science, nature communication account, like general purpose journals, and also on AI conferences, and also transportation journals. And we try to focusing on our AI plus decision-making parts and across 3 different domains. So as for my research lab right now, and I'm focusing on computing for decision-making. And I do think computing in the coming years will happen everywhere, every second. So across different platforms. So my slogans I'm keep thinking about how could we build trustworthy decision co-pilots, or we call it companion for human beings. in many of the cases, we are trying to debate ourselves on some choices. So we use our brain to do trade-offs, what-if analysis. But human brain, we just see very limited data. We build our brain and build our cognitions based on our experiences, books, and educations. If we have an AI, we should see almost all the data existing in the world. What will happen? So how could we build trustworthy AI decision co-pilots for humans? That is my research directions. So we have two tracks right now. The track one, which is trustworthy computing methods and agents. So how to build decision co-pilots for domain-specific tasks, for example, transportation and public health, to empower the decision makers. And I don't think AI will replace human beings, but they can empower us. And the track two will be efficient and sustainable computing, because if the computing happens every second on a lot of devices at every corner, actually the data center issues right now are quite a complicated thing and are also big headaches for many cities. And how could we make such a systems scale up efficiently and sustainably? That's the second part of my group are working. But for this talk, I will mainly focusing on the track one, which is how could we build up the trustworthiness and the collaborations with AI agents. So decision companions, in my thoughts, is somehow quite straightforward. We need conditional predictors. So predictions, most of the AI method, they're doing predictions, right? And we learn from the past data and we try to make some predictions happen in the future and help us to see what's going on. So that's not a new, actually, that's totally not new ideas. And the workflow will be actually not just right now, in the coming years, will be there are human decision makers. And we have customizing generative AI and agents, and they too need to work collaboratively with each other, like how we play with ChatGPT. I use GPT a lot every day, help me to organize my ideas, reply emails, and talk with my students, and even use the GPT to think how to reply with my wife's message. So there are a lot of potentials. But I think the biggest concern for human and AI, their collaboration, no matter you just consider the procedure or you consider a dialogue, you even consider a long-term coexisting process, so there will be trust. And the trust is a big concern. And if we talk about trust, and there are even very limited research and definitions to talk about to clearly give us a direction. What is trust? And before we directly talk about the works on this track, I just want to give a quick background of the generative AI. It's actually a true game changer for transportation. And some of you mentioned like there's an ongoing project within CHRP try to develop a Premier to guide the transportation planner using generative AI. And actually, there are other ongoing projects trying to try similar things. So comparing with traditional models, like the traditional machine learning models, try to find a mapping from X to Y, and actually generative AI model exhibit stronger capabilities in context generation and generalization and enabling create of text, image, music, simulations with clear potential for transportation tasks. That's for sure. I think we are experiencing such a big change right now. And the generative AI models and the generative AI capabilities. So the reasoning capability, information retrieval capabilities, editing capability, and so on and so forth, and their combinations. Right now, there's a quite popular AI agents, which is called OpenClaw. Have you guys ever tried of it? Actually, I one of my today's our group meeting, we discussed about how we can develop an open cloud, try to get the message automatically replied and your plan automatically remind, and try to coordinate with different user apps, help you to organize your workflow. And open cloud is just proposed less than 1 year, and the star on the GitHub has already surpassed the Linux system and PyTorch. So it's a quite a, I think it's a auto agent systems try to empower human beings to do something. And open cloud can even make money for you if you give a very high accessibility on your like stock account and even like the I think the bank account. It can automatically try to set up a goal, for example, like earn $20,000, and so they will put a policy for yourself and try to optimize the strategies. So I think all these kind of generative AI models and generative AI capabilities can be oversimplified on a one understanding, which is I always talk to my students, which is they are all conditional generators, no matter large language models, vision language model, AI agents. So you need to give some conditional inputs, which is closely aligned with your application's conditions. These conditions is quite complicated. Sometimes they're text, sometimes they're sequential, sometimes they're image, sometimes they're videos, but they are all conditions used as inputs. And then this model generated something based on your conditions, based on their capabilities, generative AI capabilities. It could be one capability, like just like reasoning. It also could be some combination of their capabilities. So how to improve the trust through such information inputs to give better conditions, or how to empower a more trustworthy generative capabilities is quite challenging. It's actually what we are working on. Actually, we do a lot of testing on this track. The first part is about model fine-tuning. In the past 2 years, we try to fine-tune the foundation models to help us to make safety decisions and help us to make public health decisions. And we do have some findings. The first paper, Safe Traffic Copilot, is actually the first core part of my presentation. I'll show that later. And beyond of the model fine-tuning, try to empower the more trustworthy generation process. And where the trust come from? Actually, come from our alignment of the values, right? So how could we consider integrating with human beliefs, human thoughts, and human behavior alignments into no matter the conditional inputs or the generation process is quite important. So physical alignment, testing the model performance given our physical world and also try to integrate it with our physical constraints in the generation process is the second part we are trying to working on this track. So we did some physics-informed spatial knowledge integrations actually mimic how the painters back to 500 years ago, how they organize the canvas and what are their abstracted understanding of the physical intelligence, and try to use such a procedure to empower the generative AI, and especially in the task driving procedure. So we got a lot of interesting findings. And I also have another paper which is impressed on the Trustworthy Research policy, which is there are a lot of research trying to use the LLM agents as the autonomous driving agents and control the vehicles and do some simulations. But when I first think about this research, my first fundamental question is like, LLM agents can somehow mimic human driving behavior, but to how much, to how, under what conditions it mimic better, but under what conditions not, right? So we did a primary testing on 13, 14 different LLMs and consider the information flow and the generation procedures. So we got some findings like LLM agents can partially mimic human driving behavior and decision values, but better align with aggressive profiles and especially on the turning decisions. So this paper is impressed, and there are some findings. We also talk about what are the conditional inputs to push such a human likeness, and it may help the LM simulators try to feed in with optimal information flow. And these are the two parts of the trustworthiness we try to build up: model fine-tuning and physical alignment. Actually, I think there is another quite promising direction is I think transportation, health, and network modeling people. Everybody can think about this track, which is called theory-informed reasoning. Everybody knows, like the large language model, their reasoning procedure is purely rely on text in most of the cases. So reasoning rely on text bring us a lot of flexibility, adaptability, right? We can use the richness of the text using next token prediction, try to think about vivid real world generation procedure. However, such reasoning procedure also quite lack of transparency and robustness. And one example is even you use the same input prompt to query the same models for multiple times, you still got different answers, right? So this kind of randomness and link us to think about how could we integrate some theories which can constrain the reasoning procedures and make the reasoning procedures align with human thoughts and human experiences. So we did test align with the graph theories, and we built up work which is called ego prompt. And ego prompt try to think about this way: is like after you have a prompt, And this prompt can be written in a paragraph. And we believe in such a paragraph, there could be another hidden graph-based structural knowledge. And we consider this is a semantic causal graph. It's not a causal graph, actually, because causal graph definition is quite clear. It's a semantic causal graph. And we find out such a semantic causal graph and revise the prompt automatically. So we got two results. First is effective and more efficient. And after you reorganize the prompt based on the hidden semantic graph, and you can push the small models performs even better than large models. And in this test, we found, okay, the Gemini 2.5 Flash is even better than GPT-03 and 01. And then there's a human-machine collaborative process and potential, which is the large language model have their own understanding on the backside of the hidden semantic causal things. And you may have your own semantic causal graphs, which factor may link with which factor. So you can compare to different graphs and see which one would be better. And if there's some machine editing can give you some inspirations. So this work is actually be reported by a YouTube channel, which is called Discover AI, and they make a 40 minutes video, quite a long video, to introduce our newest paper. If you have some prompts need to optimize, you also want to find some causal discovery process. I mean, it's not strictly causal discovery, but semantic causal discovery process. You can search this QR code, scan this QR code, and see how this work may align with you. And there's another task I really want to emphasize and introduce, which is the theory-informed reasoning for personalized decision-making, especially consider personalized decision-making. So in many of the cases, classic utility models, we try to model human decisions using classic theories, utility theories. And the biggest challenge is like, how could we write a utility function can well represent different choice, pros and cons, and for different individuals. And we are thinking about one step ahead, which is after we have utility functions, and we extract and abstract most of the factors into quantifiable and numerical inputs. And there do have a lot of semantic inputs, which are super hard for us to integrate into the utility functions. For example, happiness. And my wife are happy or not? It's quite some challenging task I need to guess, right? You have some semantic clues and adaptations you are thinking about. So we developed Athena, which is our 2025 newest paper published last year. Is like we are thinking about the symbolic optimization or the symbolic procedure, which is a great foundations which can help us to build the basic trust for the reasoning procedures. And then we also can integrate it with textual template optimization and try to find the best choice for the individuals, consider their own preference, intuitions, semantic feelings, and there's a co-alignment procedure here. There's another paper, so if introduced, you can go ahead and read it. So three different directions. The first is fine-tuning. If you have data, go ahead and use it. The second part is about physical alignment. And we understand the world through physical laws. So how about we do a test? We align physical information backside. And third part is about theory-informed reasoning. We have theories, we have findings. We trust these theory and findings can somehow guide our beliefs. So then how about we use such theories also help LLMs do some optimal reasoning process? So let me introduce the first part of our work, which we call Safe Traffic Copilot. And we want to do traffic crash pattern learning, causal understanding, and conditional predictions through a supervised fine-tuning procedure. And the clear target is like we want to answer two questions for safety. The first is what's going on now, and what happens if things improve. So everybody know if it's the data we collected, we make the screenshot from International Roadway Transportation Accident Database. It's an international database. We see United States crash rates. It's quite a tragedy numbers for us. And if we see the road fatalities per 1,000 inhabitants, let me find my laser pointer. In 2022, United States only can comparable with Chile, Costa Rica, and the roadway fatalities per 1,000 inhabitants is quite high. And if we compare the road fatalities per billion vehicle travels or kilometers, and we're still very bad. And if we consider comparing with UK, we're even 4 times higher than UK. However, even things even much worse than we thought, because if we see the trends comparing with other developed countries, United Kingdom, Japan, Canada, they somehow keep the pace or showing a decreased trend. However, for United States, our numbers of roadway deaths from 2012 to 2022 keep going up. It's quite weird, right? Because right now the vehicles are equipped with high technologies. We even have autonomous vehicles. And my vehicle also have equipped with collision avoidance functions. Sometimes it's quite useful. So why does this happen, actually? Um, there's also a clear chance for everybody, which is think about, I'm not sure whether I got involved into a crash, but I remember my experience after I got involved into a crash, the police officer been there, talk with me. Okay, Frank, this is a template. You need to report things based on such a template using text, right? So actually, it's bring us a natural chance to model the transportation crash using textual reasoning and textual learning. So the first responder naturally summarized the crash into reports, so they are originally text. And large language model bring us two clear new possibilities. The first is strong reasoning capabilities. Based on your conditional inputs, can the large language model have a risk assessment, how severity the crash should be? And second part is about the powerful linguistic understanding, which is they can somehow understand this is sunny day, that is a rainy day. And a sunny day and a rainy day, their impacts to the conditional text could be very different. Impact to the behavior could be very different. So could we use LLM for expected crash case modeling and predictions? And we do a test like this. So firstly, we build a multi-model crash data. Now this crash data is not just considered about text report. We also have the driver information, environmental information, state license information, and satellite images to show the large-scale planning information. And we build an LLM, fountain LLM, which is called Safe Traffic LLM. And Safe Traffic LLM is somehow like you give a prompt and you need to predict the tasks, which is the crash severity, crash type, and number of injuries to us. And you give me your confidence score and the prediction outcomes. And as I mentioned, if there is a large language model can predict this is a fatal crash for you, given conditions, and I'm pretty sure nobody will trust it unless it's tell me why that's being considered as a fatal crash, right? So we did one step ahead is we built a attribution process and try to find out 3 levels of attribution. The first is event level risk analysis and give a crash report or conditions. This condition is quite complicated. You can consider 20, 30 different sentences. So which condition is the most impact factor, which is second, and what is the combination of the impact? The second is conditional risk analysis. So after we have such a risk assessment, the next step is we try to improve our safety. We try to avoid the safety. So what if analysis and give us conditional risk analysis. And think about the third step is after you know which data will be more helpful for you to predict the severity, and which part of data will be more helpful to predict a crash type. Why not you collected more detailed of such a data type, right? So it can somehow guide the future data collection procedure for DOTs and also safety managers. And we also compare with some results across different state data collection templates. So integrating multi-model data for analysis, we have crash data, infrastructure data, vehicle data, and personal data. So we're doing data mapping and organizations try to all link with the crash ID. And then we also extract the satellite images from Google Image, and then we textualize the Google images. Is it the urban area, dense urban area, or relatively sparse urban area? Is there a shopping mall nearby? And try to show some pedestrian exposure or travel demand exposure using this kind of text, planning level information. And we also make the prompt generated. This is exactly the prompt that we use to do the predictions. And then we have multi-model crash data, finish the textualization, it look like this. And you are a helpful assistant designed to predict the target task for a traffic crash. You need to make prediction based on the information below. 4 part of information, general information. Assume a crash is expected to occur at a given time and location. What is location? What is time? What is roadway categories? Assume, as I mentioned, conditional generator conditions. Infrastructure information. Assume the crash is expected to occur in the following infrastructure: roadway width, roadway surface, and roadway is concrete, asphalt. You can put as much infrastructure information as you can. And how about infrastructure conditions? Is not medium separated. Medium separated is 2-lane, 3-lane, is highway, it's like urban arterial road, something like that. And then event information. Assume the spatial temporal location, spatial temporal points you want to do the predictions. There are no pedestrian involved. How many vehicles involved? And is this accident influenced by alcohol or drugs? And if yes, how much? Remember, these are all assumptions, and you can easily change these assumptions and redo the prediction, like how you write prompts every day. And unit information, how about vehicle 1, driver 1, conditions for about vehicle 2 and driver 2. And we try to predict 3 different categories of our targets: crash injury, second is crash severity, and the third is crash type. For crash injury, we have 4 categories: 0 injuries, 1 injuries, 2 injuries, and more than 3 and more than 3 injuries. For severity, there are 5 different categories: no apparent injury, possible injury, injury, serious injury, and fatal. For crash type, there are 14 different categories, and we fine-tuned the large language model based on the real-world collected data. So this is exactly the predicted targets and the data we tested here. So we use the Washington State crash records and Illinois State crash records to fine-tune the model and validate and testing the model. And these are the all exacted predicted outcomes categories and classification categories. Accident type 14, severity crash 5, number of people injured, we have 4 categories. And we not just test our results, predictions in Washington State and Illinois State. We also tested in North Carolina, Maine, and Ohio. And there are some interesting findings. This is exactly how we do the fine-tuning. Actually, the fine-tuning work is not novel at all, in my thoughts. And we use the low-rank adaptation fine-tune process. And the overall idea can consider like this. You have a quite big pre-trained weight matrix. And right now, you want to train a low-rank matrix serve as a bias for such a domain-specific task. I always introduce this process. It's like we teach the large language model to pass a graduate study based on our own collected data, based on a low-rank adaptation process. And then the model shows some performance. The first, the safe traffic copilots perform best among different states, 5 states, and compare with all the existing works, no matter it's BERT, table nets, and national baseline through the NCHRP report or some statistical model. It should be, and it's much more performed. That's the first thing. And if it's just here, it's not that noticeable. But we do have some interesting findings. The first findings is like it provides our truly trustworthy predictions from several perspectives. The first perspective you can think about, everybody, if you have predicted results, you want to set up a threshold. Some of the predictions you are just like hallucination, but some of the predictions really helpful. So how could we set up some threshold that is after the model have more than 80% of the confidence score, I can treat it very seriously, this model prediction can be useful. So I see a clearly trend of increase on 3 different tasks. On the figure E and figure F, you can think the axis is a confidence threshold, and the Y is a model precision on 3 different prediction tasks on Washington and the Illinois dataset. And there's a clear increasement, which is if you set up a higher confidence score, you got a better precision. I never saw such a trend, linear alignment of the confidence score threshold increasement. You got higher precisions and accuracies of model predictions in the traditional machine learning models. Not traditional, but also deep learning models like the LSTM and other type of models. The first time I saw. And second part, if you think about crash prediction, fatal crash is naturally more challenging because you just have limited data. For sure, right? Fatal crash only consider around like 0.1% of the data collected in this data set. But the large language model performs higher prediction performance for fatal crash, much higher. Means what? Actually, they are trying to do reasoning tasks from the conditions to the outcomes. I give you such an output, which is based on such conditions you give to me, and I analyze different conditions and think about this, it's a fatal crash. So the average prediction accuracy on two states, Washington and Illinois, the fatal crash is much higher than average. And if you consider the fatal crash threshold, it's also higher than average. And this tells us actually, after you fine-tune the large language model, you can get a better graduate student, I mean, trained from such a specific task, but still can understand the textual reason, textual meaning, and tokenization embeddings based on the language training process. And we also tested from 2019, 2021, and the prediction on Washington State is quite stable. And we also do zero-shot state. You see, in North Carolina, Maine, and Ohio, this model never seen the data from such three states. Maine state is quite cold during the winter season. The distribution somehow quite shift a lot. North Carolina located at like the southeast part of the United States. They also have different weather conditions in summer situations. So the model also can handle such an unseen scenarios. So this is the first thing I would like to highlight, give us some trustworthy predictions. And the second part I want to introduce is like how we do attributions. So we are thinking about the input prompt. Such a prompt is like a multiplayer games. And we consider every sentence actually is a contributing player to the predictions. So there's a natural framework for us to do estimate attributions, which we call Shapley values. So Shapley values is like a method for cooperative game theory, which we can consider as a fairly distributed total gain among all players based on their contributions. So we set up different collisions, and every unit, every sentence, you with this sentence and without sentences, you search all the collisions and try to estimate all the contributions based on different collisions. So we got Shapley values. And the biggest challenge for this part is like the input prompts length is quite different. Some of the prompt, I remember there is a case in Illinois, 17 vehicles involved. The prompt is more than 70,000 words. Some of the cases, their prompt is just quite low, 200, 300 words. So we propose somehow we call sentential Shapley, and we try to align every sentences give you a tag. And so all the sentences you describe location time, no matter you just have one sentence or two sentences, we consider it's a tag. And then we calculate the sentence level of Shapley features contributions. And we got what? We got exactly what we want. If we have such a template, if we have such a crash report, this crash report is 300 words, 500 words, and different language descriptions. And we want to know which factor contribute how much, positive or negative, to the target, predicted target, which is a serious injury crash. And let's see, this is a real-world crash report in Washington State. And we categorize them into 14 different categories: location, time, roadway class, intersection related information, traffic characteristics, blah, blah, blah. And we quantify every parameters, their contributions based on Shapley values. And we found the driver behavior and person information contributes the most to such a serious injury crash. Why? Let's look back. Because the driver is like operating recklessly or aggressively and no restricted used. Okay. And there's another report in Illinois state, actually it's a fatal crash. And the biggest semantic reasons here is because access control and work zone. So the work zone safety is quite important. And actually in our paper appendix, we have around, I remember we have at least 20, 30 different cases visualized like this. So you can think about and really think about that. And one more thing I want to highlight is this figure. After you have such a sentential level Shapley attribution, so one step ahead, you can do a risky ranking, right? You have all the high risky conditions and their combinations. You can rank from the most risky scenarios to the minimal risky scenarios and try to find out their transitions and differences and which part of data contribute to how much. And after you know which part of the information contribute to the risky level to how much, you can easily guide the training procedure because you can revise the textual template, tell the police officer. I will use a real example for the Illinois state and Washington state. They're different recorded for the alcohol blood contents information. In the Washington state, they just have yes or no. But in the Illinois state, they have a clear blood content alcohol numbers like here. So there's a clear record here. And for the Washington state, they're just like yes or no, something like that. And alcohol involved, so there's no pedestrian involved, two vehicles involved, no influence of alcohol drugs. But for Illinois, they have a clear number. And we found very clear differences on these two states' Shapley attributions for the alcohol and driver BACs. See here, the driver's blood content was tested measured 0.203, and the contribution is quite clear. So it can push us one step ahead. Is like if such an information can provide more values and have a human proxy cognitive agents we call LM, probably it will be much more helpful for us to record it in more details through the training procedure. So key takeaways from this paper: if you have accumulated data and clear application scenarios, trust me, learn from the data through model fine-tuning for task adaptation is quite a straightforward idea, but you can get better performance. And in most of the cases, you can get great trustworthiness. And you even can get better generalization on your own task. Also, a lot of unseen scenarios, because generalization is exactly the advantages for large language model. However, you need high computational cost and high demand for data. And this is quite a disadvantage. And the second quite challenge is about transparency. Even we have attributions, but we do have no idea how the model reasoned out such attributions, right? So we want to introduce one of our ongoing research, which we call personalized decision strategies, and it can be transparentified, we call it crystallized through the due evolution of behavior theories and language models. Actually, this work is a follow-up work from Athena. I will introduce them together. The idea is actually from a book. Recently, I read it. And I think many of you, especially Manshi, might quite familiar with this behavior theory book and Daniel Kahneman. So he has the book quite called Think Fast and Slow. And the hidden thoughts like for every human beings, when we're doing decisions, actually, we have two brains, two mindset. One is very fast, intuitive, another is slow and analytical. And these two mindsets compete with each other, and we finally got a decision. Another quite inspiring research paper is actually happening in California. Dr. Scott Muller and Julie Pirro, and pretty sure many of you have heard about Dr. Julie Pirro, is a Turing Award winner. He proposed a concept in 2022 called personalized decision making. He's trying to think about using the causal inference theory and the causal models to leveraging individual level decision support or subgroups. And these two research bring me to think about a dilemma, which is generalization and personalization. In our daily lifetime, we need to change our job, we move to a city, and when you got a vaccine, use pain reliever, or take buses, driving by my own vehicles, there are always a generalized concern and a personalized concern. So, and how could we model human complex decisions, try to do trade-offs? We align with general values, and we also align with my personal preference. It's quite challenging. So actually, the classic LM, the classic models, utility-based theories like multinomial logic, nested logic, mixed logic, and also the prospect theories, and this kind of utility function modeling, they try to do human-like human utility function making, and there are two basic assumptions. The first, like they try to model things on population level, because utility function, if you just model one person of utility, like I think you can easily write a prompt. You can easily write a utility function for my dog, because it's the cognitive process is quite straightforward and easy. However, if you want to write individual level of utility functions, so challenging, right? So focus on population level. And the second basic assumption in most of utility theories, like they're rational assumptions. They're not considered about like preference, human semantic happiness, something like that, stable preferences. And these are classic models. However, for large language models, there are some clear advantages. The first advantage is about open world generation. They can handle a lot of unseen scenarios, new scenarios, even they are not rational. Even they are not population level statistical obvious outliers, actually. That part of outliers are actually something we try to eliminate through the statistical procedure. And also individual preferences. And large language models are quite beautiful for modeling the individual preferences. Sometimes you are elder people, younger people, and you have clear different mindset. You want to choose different choices. No problem. Large language model can help you. The only requirements are like you provide a clear conditional inputs or learning process. But large language model have a clear constraints, which is transparency. You give me outputs. I have no idea where have this output come from. And also randomness. I mentioned this before. You give the same prompts, same conditions, and the model still can give you different outputs. So, this combination is quite straightforward. Can we align these two approaches together? But the task is quite challenging. We have individual attributes, and we have structure and quantifiable factors through the utility theory, and plus with preference and semantic feeding through large language models. And if we can align these two parts together in a unified reasoning engine, that's beautiful. That's our human brains, right? So we did the first task of Athena, model both structured and quantified and unstructured semantic attributes together through the large language models. How we do that? Is actually we build everything based on such a conditional generations. The first thing is we try to find the best symbolic utility functions and use such a symbolic utility functions to guide the symbolic optimization and try to find some group level of optimal points. And then we try to integrate the semantic information, semantic richness using textual data and try to link with the best local optimal points for such individuals. That is what we are doing, what we have already tested. And actually, we achieve such a procedure purely through LLM. Even the symbolic utility functions, we use the LLM to write symbolic utility functions for us. The utility functions written by the LLM, it's a quite a magic process. Previously, we try to aggregate the utility functions. It's quite hard for us doing the procedure, but we can easily ask the language model to write 20, 30, 50 different utilities, and we choose the best top three and do another iteration, and then write 50 and choose the top three, do another level iteration. Actually, there are a lot of people working on this track on the reinforcement learning with human feedbacks. And we have some limitations find the utility function writing purely just by LM, by the prompt. It's quite adaptive, but this utility function is still super complex, involving like nested square rules plus rules, and also nested logs, and also plus with sigma functions. Sigma functions actually like activation functions in the neural networks. Actually, they're trying to understand the modeling, writing the utility behaviors based on the machine intelligence, not quite aligned with human beliefs, and which makes us very hard to understand it. But the motivation for us try to integrate with theories like we want the transparency. At least you should follow our common thoughts or common rules, right? And another clear disadvantage for Athena is not stable. It's very hard to train and very hard to find through such a group level symbolic utility discovery. we introduced a lot of details in this paper. So if you're interested with this paper, please go ahead and read it. And it's lucky enough to be selected as the spotlight paper on the Neuros 2025. So after we think about this, we reread the paper, we reread the book, which is called Think Fast and Slow, proposed by the Dr. Daniel Kahneman. And every human beings, when we try to make decisions, we have two debating internal systems, intuitions, and try to push us make decisions fast, quick, based on semantic support. And then sometimes we also have a deliberation procedure or analytical procedure. For example, should we work remote or on-site? Our intuitions right now, at least for me, traveling across the whole Baltimore city every day, congested and unsafe, makes me really prefer work remote. However, remote work may got lower pay or may got limited social scope. Well, there is a procedure for such two intuitions play with the deliberations, analyticals, and think fast and slow. And actually, there are two systems backside. The Dr. Kahneman mentioned this in the book. The system one is called intuitions and preference system. Act fast, automatic, and it's actually work based on the heuristic and experience based. There's a hidden intuitions, hidden experience based functions, utilities, memorized by your head. And once you match such a situation, you have intention. And also you have initial choice and tendencies. You gradually updated your hidden experience intentions, like year by year, quite long. Not every second for sure, not every day for There's another system we call deliberation and reasoning system. They're quite slow and analytical, try to deliver goal-oriented and conditional analysis, try to evaluate different trade-offs, what-if analysis, like what we did for the safe traffic copilots, right? And it's reflectively update through the reasoning procedure. For example, after you talk with your wife, talk with your family, you may change your mind. You got new inputs. You updated your deliberation and the reasoning situations. So can we unify the two systems through the most powerful AI engine, which is foundation model? And actually, we do a test like this. But the challenges are clear. Three parts. The first is how we align with math and text. If we align too much with math, utility function is driven, right? If we align too much with text, it's too adaptive, still not transparent, not robust. And the second part is about personalization and transparency. Athena tells us the large language model even can write a very personalized utility functions for subgroups if your group just have 20 cases, even 30 cases. However, it's still hard to understand. If we want transparency, we want a reasoning-based, trackable reasoning record, we need to do trade-offs. And third part is about robustness. It still can be summarized into another side effects for the math and text. Robust, for sure. Math, we have bounds, upper bounds, lower bounds from such a theory. But for like LMs, very hard. So we propose a framework which is called DualMind for AI agents. And these DualMind AI agents are directly inspired by human, like fast and slow thinking procedure. And human inputs, think about we have two parts of inputs: sensory, preference, experience, and we also symbolic knowledge rules. And these two parts combined integrated into two procedures. The first is intuitive and preference procedure. It's quite fast, automatic, implicit, right? Heuristic and intuitive process. And then the heuristic intuitive process put into analytical reflective process, past a slow, logical, deliberative process, and then we're doing final decisions. So actually our final decision is guided by two parts information. The first is like personalized hidden intuitions. That's hidden intuitions. Yeah, very hard to, say it, but you accumulated hidden intuitions, like hidden functions on your brain. And once you encounter such a situation, you have something showing immediately, and then conditional analysis trade-offs. So we achieve such a procedure in the like a novel gradient procedure. We call it DualMind gradient. So DualMind gradients you can consider into two parts. The first part is also human-like inputs. You have raw data, tendencies, and experiences cases. And then you have textual data, knowledge set, preference, personalized informations. And these two information are reasoning by two parts of two different engines, simulate the two process. The first part is about theories, behavioral theories. We try to write a personalized hidden utility functions to mimic the intuitive procedure, fast, automatic, implicit, like stereotypic. If such a function has been cultivated, it's quite hard for you to update that just based on your conditional analysis. And then you also have a super powerful analytical engine, and you can accept the external feelings, language outputs, dialogues, conditions using your large language models, try to mimic the analytical procedures we call DualMind, forward, and the gradient. So finally, we got personalized hidden utility functions, UX, and we also got the personalized reasoning knowledge. So this is the output. I think I should speed up a little bit. This is what the DualMind reasoning and the gradient we achieve. So at every step T, you have two procedures: DualMind forward reasoning and DualMind gradient. So one step ahead and optimization back. So at DualMind forward reasoning, your utility functions and raw data generate a string vector for you. It's a utility functions. It's actually intuitions, right? We try to think something like work from home or work on site, we have a natural preference. And this is a string vector. At least if I choose to work from home, I exactly will analyze the advantages of work from home. String vector guided me to doing forward thinking on that track. And then you have another part of inputs, which is knowledge set and textualized set, showing the real world richness for you for the LLMs. And then this LLM will not just independently thinking. It will think based on the stirring vector impacts. So we think the stirring vector used as intuitions to impact your reasoning directions. And so you have utility stirred LLM to control your reasoning direction and thoughts. And demand gradient is another thing I really want to share our findings like. Actually, we are concerned about the utility function, the theory's role, plus with the knowledge and textual information's role. When we're doing decisions, actually utility functions, we calculate the clear equations and we want to calculate the stock, the price, the bonus, for sure, right? Salaries, monthly income, we have equations. This can be summarized in the utility function, no problem. Knowledge, the culture of some like institutions, the culture of your workplace, relationships, something super hard for you to have a quantitative method and you have semantic understandings. So you have gradient knowledge parts you can update. Are the utility functions showing impacts to the knowledge? For sure. Sometimes if some vectors you integrated into your intuitions is not good enough, you still want to emphasize such an impact on your semantic feelings, right? So that's the co-gradient for knowledge represented utility functions. Sometimes your knowledge side impacts your worthy of analysis can be summarized and updated into your intuitions. For example, if you have a long-term updates all follow one direction, you may update your intuitions based on previous several steps update and update your utility functions represent your hidden intuitions. Forward reasoning and backward gradient. So actually, this is how we achieve this. Our forward reasoning prompt template is like your travel mode choice decision assistant, you have task descriptions, you have your knowledge set, you have your utility functions, which is exactly initialized based on utility summarization. That is exactly the utility function, no difference with the Python or GPLN, their utility theory writings. And then you can generate a dynamic stirring vector based on this vector combination through the utility function calculations and try to guide how the LLM doing reasoning. So utility function, their corresponding string vector, get LLM reasoning analogs to intuitions guiding deliberations. And then gradient, as I mentioned, 4 parts. You have knowledge mind and you have utility mind. So knowledge mind means consider how income levels, educations influence travel mode preferences, updated your knowledge set. And you also have your utility gradient, try to update your hidden utility functions. And your co-gradient for knowledge, which is you use knowledge to represent some utility functions, which is not enough for you just consider such function in your utility. And the co-gradient for utility is like you summarize some high-level knowledge information or experienced information to update your hidden intuitions. So we align such a procedure by utility gradient, knowledge gradient, and co-gradient. And you may curious about how we do knowledge gradient. It's textual gradient, right? How we calculate the gradient law, something like that. In 2025, there's a paper called Textual Gradient published by Dr. James Zhou from Stanford University. They designed a textual gradient template for such a process. If you're interested, please go and read it. And you can consider it's like using every prompt like inputs and combinations. And doing updates, Dillman forward reasoning gradient. And we tested such a Dillman process on 6 different real-world data sets across daily decisions, alcohol use, job choice and travel mode choice, and medical decisions, marijuana, vaccine intake, and pain reliever. And we cut for every decisions, we cut into 9 different groups based on your age and based on your income, try to personalize your decisions based on subgroup. Results, okay, exciting and interesting. So 42.8% of the F1 score increasement compared with vanilla LLMs. So we consider 4 different types of LLMs, GPT-4o, GPT Mini, Gemini, DeepSeek, and also other type of LLMs. We just do not release them. We don't want to make the figure too long. And actually, there are more than half percent of the improvements are
Right.
bring by such a. Go ahead. Sorry.
Sorry, we're a bit over time. Is it okay if you maybe finish in 2, 3 minutes?
Of course. Of course. That is my plan also, I see. Just have 2 or 3 slides later.
Okay, thank you.
Yes. Yes. And there's also a little bit more stability because you have a Stirling vector gradient. And then if we compare the models performance with traditional models and the Python and GPLN truly utility functions, you can find it is like the performance is better and it's truly based on some utility functions preferences. And there's also clear findings, which is complementary of utility models and LLMs. And low confidence for the utility-based models, and we got very high performance based on LLM performance. But high confidence for utility-based models, lower performance for LLM models, and based on different groups. And you can see this figure, this is a purely LLM only, and like the blue square is the purely utility only. And the model is trying to capture the synergy for both type of like reasoning process. And this is the last image I want to really share, which is if you're doing analysis on different groups, I think this figure is actually, and you can find out the Y means young, M means middle, and O means old, 3 different age groups. And there are 3 different level groups, high income, medium income, low income. Some of the groups, they're quite utility dominated. You write an utility function, okay, and this group behaviors you can capture a lot. But for many of the young low-income groups and young high-income groups and some medium, like middle classes, their choices are super hard for you just to use utility-based models. And such a procedure can also be summarized in the transparent evolution process. There are the details. And this paper, we are still summarizing it, but some findings just want to share, like the annual income. It's not just sufficient for you to integrate it in the utility functions. In many of the cases, annual income also need to be integrated in your textual impacts and showing the synergy impacts in both of the utility mind and knowledge mind. So some ongoing works, and let me share my future vision of the AI and the human process. So in the coming years, my thoughts are like AI are not truly working for us. They are work with us. They're companions, they're co-pilots, they're somehow decision referees. They can generate something we can think and use. I also want to use the last slide to acknowledge my sponsors, collaborators, and my great students, and also my quirky. Provide a lot of emotional and semantic support for me. And that's all. Thank you so much for everyone. Sorry, a little bit over time. Yeah. Happy for open for questions, please.
Maybe we can have like 1 to 2 questions from the audience. Yes, please.
Professor Yang, thank you. My question is somewhat straightforward. So I'm interested in the safe traffic LLM and that finding that you showed where there was an accuracy improvement for fatal crashes. And I was wondering if that scaled with the accident severity. That was something you didn't touch upon. So you did talk later about severe injury accidents, but I was wondering, does that result scale? In other words, is it more accurate for severe injury collisions as opposed to no injury collisions? Because
Good points.
I'm wondering if the quality of the training reports has anything to do, because usually accident report or collision reports that have more severe injuries or fatal collisions have more details provided in the report. So that's where I'm getting to with this question.
That's a great point, actually. So you're mentioning this figure, right? And you want to extend into other type of crash types, right? And I just analyzed it. I merged the fatal crashes and serious injuries together for this conditional risk assessment. For injury and no injury crashes, and we did a test, but we do not find quite a clear pattern of the impact features. And there's another big challenge for us, which is how to do sharply value collisions, setup. And for like the such a fatal crashes, we just summarize 5 like high risk factors: driving behavior, the pedestrian cyclist involved or not, work zone involved or not, freeway yes or no, and different blood alcohol content level. However, for non-apparent injury and just injury crashes, there are more than like 20, 30, even 40 different factors may show some influence for the results. And if we just use Sharpe value estimation, it's 2 power 20, 2 power 40 different combinations. It makes the calculations impossible. And so that's another quite challenging scenarios for we are modeling the non-apparent injury things. So I think there will be some other like approaches can reduce the dimensionality and reduce the complexity for calculations. But we haven't done that yet. And you may download the data and have a try to find somehow to see. Yeah.
Any other quick question? So I have a quick question. So when you compute the Shapley value, like it's a calculation based on the numeric score, right? So if you
Yes.
change your scoring system, then your Shapley value ranking may not change, but the absolute value will
Change.
can be quite different, right? So how do
Yes.
you make sure that the selection of this scoring rule is suitable?
So we try all the potential combinations, and the risk level is exactly the model confidence score.
Okay.
Because
Okay.
we previously have a confidence score linked with the like precision. So we use a confidence score as an indicator for the risky assessment. Great
Okay.
question, Mike. Yeah.
Okay, thank you.
Actually, we also choose we do not use all the testing results. We just use the corrected predictions to calculate the Sharpe value.
Sure.
Yeah.
Sure.
Yeah, we're doing the filtering of the prediction results.
Okay.
Go
Thank
ahead.
you.
Sorry.
So for the interest of time, maybe we're going to wrap up. Okay, then we're going to wrap up. So let's thank our speaker again. And if you have more questions, like you can communicate with us.
Thank you. I think I can share the slides to you, and if you're interested, feel free to reach out. Have a great day, everybody.
Thank you. Thanks so much.
Great
So
work.
wonderful talk.
Thank you.
Yeah, thank you. Great.
Bye.